So in this video, I'm going to be going over this differential equation challenge that I made. And I'm going to do it in two videos. The first one's going to look at the slope field and particular solution to this problem, as well as looking at Euler's method approximations and Taylor series approximations to a particular solution. And then the second video, I'm going to look at the actual analytical solution, and then we can compare which approximation was better. So let's get right into it here. 1a says, the image below is the slope field for this differential equation. Sketch the isocline for dy by dx equals 0. So we know that dy by dx equals x cos y. And this will equal 0 whenever either of these factors equals 0. And so obviously the first factor will be when x equals 0. So the isocline we can put in for that is going to be a straight line at x equals 0, going right down here. And then the next factor is going to be when cos y equals 0. So let's say we draw a unit circle, and we know that cosine is going to equal 0 at these points here, whenever it's at the top of the circle. When it's going to be at pi over 2, 3 pi over 2, etc. Whenever you have pi over 2 plus k pi, where k is an integer. Now if we look at the range of our slope field here, it looks like it's going between about 2 pi and negative 2 pi. So we're going to be interested in the solutions pi over 2 and 3 pi over 2, as well as the negative versions of those. So this is going to occur whenever y equals plus or minus pi over 2 and plus or minus 3 pi over 2. That's going to be when dy by dx equals 0. So we can sketch these isoclines into our solution here. So the first one, pi over 2, occurs approximately here. You can see the slope field lines really start to flatten out there. And then the next one occurs at about 3 pi over 2. It really starts to occur right around here. Now if we just do the same for the negative version, the first isocline will be at negative pi over 2, which is about here. And we also have another one at negative 3 pi over 2, which is down about here. And so that's all the isoclines for this differential equation on the slope field. So part B now says, sketch the particular solution. And in this case, we're given the initial condition y of 1 equals 0. So we're interested in the solution curve, which is going to have the point 1, 0. So I'm going to change my color here. Let's say I make this in green, so it's a little easier to see. So we know that 1, 0 looks like it's about here on our slope field. And if we just kind of follow the lines, we can see that it sort of does something like this. It dips down, flattens out, and comes back up top there. So this here is the particular solution for this differential equation. So now 2a says to use Euler's method with step size 0.1 to approximate y of 1.4. So we know that dy by dx equals x cos y. And we know that h, our step size, is equal to 0.1. So now what you have to do is you have to go through the table here and use the usual steps for Euler's method to determine the estimated value with the step size 0.1. So I'm going to go ahead and fill out this table. I'm going to take a minute and do it yourself. So these values here will be 1.1, 1.2, 1.3, 1.4. And then over here, if you work through this equation, I'll just skip ahead for the sake of time. But you just follow through the steps, and you're going to get approximately 0.1, 0.21, 0.33, and 0.45. That's just rounding these numbers. But if you were to use the actual answer, if you use your calculator memory button when you're going through these calculations in order to make sure you don't have any inaccuracy, you're going to find that this will give you an approximate value of y of 1.4 is approximately equal to 0.4499464,095. That's the estimate you're going to get if you use Euler's method with the step size of 0.1. So the second way of estimating the solution to this differential equation, which I'll just write again here, dy by dx equals x cos y, y of 1 equals 0. The other way to do it is to use a Taylor series polynomial about the point x equals 1. So what we can do is we know that our usual Taylor series formula, Tn of x about a, is the expansion out here. But we know that y of 1 equals 0. We know that dy by dx equals cos y minus x sine y times dy by dx. And then if we differentiate this, we're going to get the second derivative, d2y by dx squared, is going to be equal to negative sine y. Oops, no, it's not going to be that. It's going to be equal to cos y. Oh, wait, what am I doing here? No. We have to put this instead. dy by dx equals x cos y. d2y by dx squared equals cos y minus x sine y times dy by dx. And then our third derivative is going to be equal to negative sine y times dy by dx plus negative sine y minus x cos y times dy by dx. This is using the product rule and the chain rule. Then that's times dy by dx, and then minus x sine y times the second derivative of y with respect to x. So obviously the derivatives get quite nasty here, and you wouldn't really want to go by hand any further than the third derivative. So once you do that, now you can actually substitute the point for the initial condition, which is when x is 1 and y equals 0. So if you do that, what you're going to find is that obviously y of 1 equals 0, dy by dx at x equals 1 is going to equal 1. And then the second derivative, d2y by dx squared, is also going to equal 1. And then the third derivative is going to equal negative 1. This is just if you substitute the points in for this. And you'll get that these are your coefficients in your Taylor series. So now that you have this, you can actually construct the third degree Taylor polynomial. So we're going to have the third Taylor polynomial about x equals 1 is equal to our first term, which is 0. So we're going to get 0 plus 1 times x minus 1 to the 1 over 1 factorial plus 1 times x minus 2 squared over 2 factorial minus x minus 1. Well, it shouldn't be 2 over here. It should be a 1 minus x minus 1 cubed over top of 3 factorial. And so if we just simplify this out a little bit, I won't expand it, but I'll just write it a bit more nicely. We're going to get x minus 1 plus x minus 1 squared over 2 minus x minus 1 cubed over 6. And if we substitute our point 1.4, which is what we want to approximate, so we're looking for the third degree Taylor polynomial of 1.4 about 1. This will equal 1.4 minus 1 plus 1.4 minus 1 squared over 2 minus 1.4 minus 1 cubed over 6, which is approximately equal to 0.4693333, and the 3 will just keep repeating. So I might as well put 7 3s in here, because that's what a usual calculator display will show. So that's the approximation you get with a third degree Taylor polynomial. And in the next video, I'm going to be going over the analytical solution, and then once we find the actual solution, we will compare which of our approximations here was more accurate.